hello, a very warm welcome. It's a bit uncomfortable for me to be speaking in English in the Westerkerk in Leeuwarden, in Leeuwarden. But a very warm welcome to this very special evening, I think. I'm happy to introduce Amina Helmi later, but first let me say a few words about the evening itself. And my mother always told me, don't forget to introduce yourself. So my name is Arjen Dijkstra. I work at the University of Groningen, but I've done a lot of research as a history of science into the practice of astronomy in the province of Friesland. So in this province, in the area we are right now. Tonight is a night, an evening organized by Studium Generale Leeuwarden, Studium Generale Groningen, and Explore the North. And they are organizing a few evenings on astronomy or topics related to astronomy. Last week we had Frank Westerman talking about his new book, The Cosmic Comedy. And next week, Marjolein van Heemstra will be giving a solo performance in Dutch called Stadsastronaut, City Astronaut. Marjolein van Heemstra just wrote a book, In Light Years Nobody is Hastily, I think. Niemand heeft haast in lichtjaren, which is a bit odd because light years is a distance and not a time, but... Tonight, Amina Helmi will be speaking. Amina Helmi is one of the most prominent researchers of Groningen University, one of the most prominent astronomers working in the Netherlands. And that's quite an achievement, because if there's one field in science the Dutch universities are really good at, it's astronomy. So I'm always impressed by, I've had the privilege of hearing her talk a few times, and I'm always impressed by the results and the way she works and the magnificent stories she tells about the archaeology of our own universe, about how everything happened a long time ago. And I want to take you back to the early 17th century, because there's a relation to Friesland and your research you may not know, Amina. In the early 17th century, in 1608 to be precise, the telescope was invented. And this was the first time that mankind could look up to the stars and actually bring the stars a little bit closer, start studying it. It's quite a mystery who actually invented the telescope, but we know for certain that the professor of astronomy of the University of Franeker, which is a town close to Leeuwarden, his brother invented an instrument that was a telescope. What we also know for certain is that one of his students arrived in northern Italy in the summer of 1609. Later, this student would claim he handed his telescope, which he had brought from the Netherlands, to a certain guy called Galileo, whom you all may know. And Galileo too pointed the telescope to the skies, and then he thought, well, this is not a good instrument, and he improved it. And with his new and improved telescope, he started the first research project into the skies using a telescope. And that, I think, sets the scene for the work Amina does, because it looks like this, but it also very much doesn't look like this. So, Amina, the floor is yours.
Thanks, Arjen, for the very nice introduction, for the welcoming words, and thanks everybody for being today here. What I wanted to talk about today is archaeology with stars. And what do I mean by that? I mean trying to use stars to figure out, as if they were artifacts, as if they are fossils, to try to figure out how the Milky Way, how our own galaxy was put together. But before I do that, what I wanted to do is I wanted to pose pause a minute, stop a minute on this picture. This works. Okay, takes a while. So this is one of my favorite pictures in astronomy. And the reason for that is what you see here is the Milky Way as you see it from the southern hemisphere. So you see the magnificence of the sky, of the universe, basically a window into the universe. And then you see this small telescope, this dome on top of a mountain in Chile. And where there is somebody that night observing the sky, doing a measurement, an astronomical measurement, and trying to figure out something about the universe. And what this picture for me embodies is a very big contrast between, the immensity of the universe and this little person, somebody like one of us, particularly close, somebody like me, an astronomer, trying to understand how it all was put together. And I think, that contrast in scales is extremely large, makes you humble, but at the same time, the fact that we can, with the laws of physics, understand how something like the Milky Way was put together, I think that's something that is very, to me at least, very touching and very motivating. Okay, so what you see here is the Milky Way from different locations on Earth. First, you see how the Milky Way looks like from Tenerife, a place where there are many telescopes that we use to study the universe. You see the Milky Way from Argentina, which is actually where I come from, and you can also see it in great splendor. And then you see the Milky Way from space. You can actually see its structure much better. Here you see just a portion of the Milky Way, depending on where you are on Earth. So from space, we see it much, much better. And then you can also see it from the Netherlands, and then, okay, it's not quite the same thing. But maybe, when you leave this lecture this evening, you can look up the sky and actually see it as well. So, it's not hopeless in days and nights like today's. So what is the Milky Way? So I think I'll, yes. So the Milky Way is a conglomerate of stars. So this whitish band that you see on the sky is actually a conglomerate of billions of stars. So if we zoom in, and the more we zoom in, the more stars we see. So we see lots of stars, and because they are so far away, when you look at the sky, they appear to be a whitish band on the sky. But it's really a composition of stars, a lot of dust. So these regions, these dark regions, are dusty regions where new stars are being formed. A lot of gas, from which also stars are formed. And also, around the Milky Way, what we have is dark matter, which is a very mysterious component of the universe, but that makes most of the mass of the universe. I'm not going to talk about dark matter today. I'm going to focus on stars. These dark regions, as I was saying, are regions where new stars are being born in these dark clouds. We see new stars born, and we see them actually not born in isolation, but born in groups. And we see also that many of these stars, when they are born, also planets are born around them. So the Milky Way is this conglomerate of stars, planets, gas, dust, the dark matter. It's some kind of ecosystem, but this is what we call a galaxy. So the Milky Way is just a galaxy, like hundreds of millions of galaxies in the universe. What we see, it has this kind of pancake form. It's a disk galaxy, and the reason we see this kind of, if you look up in the sky, you see a region where you see more stars, this whitish band, it's because you're seeing basically the galaxy. We're sitting in that pancake here, and so you see it edge on. If we were able to move away from the galaxy up, then we would see something like this, as shown in this picture, another galaxy in the universe. If we were outside of the Milky Way, then we would see something like this. So the Milky Way is a simple galaxy. It's actually a typical galaxy. There are many galaxies in the universe like ours. Some of the galaxies look rather differently, but the Milky Way is a disk, and this type of galaxy, roughly 2/3 of all galaxies or large galaxies in the universe are like the Milky Way. So in that context, it's very typical, also in terms of how bright it is, how many stars there are, how large it is. It's a very common system. But what's special about the Milky Way is actually that we can study it in a lot more detail. And we have access through this information that we have to the ability of understanding how all galaxies in the universe form. Just because it's typical, we can use it as a prototype to understand galaxy formation. We can use it to understand the physical processes that take place in a galaxy, the physical processes that lead to the formation of stars, for example. And we can also use it to understand what the universe is made of. So, for example, this, what I mentioned, the dark matter, is something that was also discovered through the motions of stars in our galaxy. But the reason I am mostly fascinated about the Milky Way is that the Milky Way is our home in the universe. And so like we try to understand our own origins, we're interested in, who our parents were, grandparents, we're interested in knowing what our origin is, where do we come from. I'm also interested from that perspective in the Milky Way and in understanding how the Milky Way was put together and what its history is. And so we have, I guess the range is not large enough to actually work properly. So we have an idea of, we have the hot Big Bang model of the universe, actually, that starts with a Big Bang. It's an explosion. The universe starts. It expands very quickly from the early days. And in that, say, Big Bang, the first elements like hydrogen and helium are formed. It's a very hot configuration, and that energy kind of drives that expansion of the universe, and as the universe cools down, basically the first stars and the first galaxies form. So we have evidence of those first galaxies. This isn't working at all. We have evidence of those first galaxies through observations of very, very faint objects that lie very, very far away from us. So you must realize, you probably know, that if we look at the sun, when we see the sun today, actually it is how the sun looked like 8 minutes ago. So it takes a while before the light from the sun reaches us. Now, for another star that's even farther away, it will maybe take years for us to reach that light to reach us. So the farther you put the object, basically, the more you're looking into the past. And so when we look at very distant galaxies, we're really observing galaxies, or how they were in the very early stages of the universe. And so a galaxy like this is a galaxy that was born something like 1 billion years after the Big Bang. Now, the universe is something like almost 14 billion years old. So this is fairly early on in the history. It's as far as we can go with the current telescopes. And so what you see here is you basically see a blob. You don't see much more than that. So there's not a lot of information that you can get from observing this object, except that it was there. right? So galaxies were already forming very early on in the universe. If you go forward in time, then actually what you see is that if you come closer to the present day, then what you see is that galaxies are typically not in isolation, but they often interact with each other. So that's a process throughout which apparently galaxies form. And then we come to the present day, and we come to the Milky Way. And what's interesting, so we have a large variety of galaxies around us, but in particular for the Milky Way, as you saw in those pictures, we can see the individual stars. So we know how stars are moving in this system. This is something that we cannot do for other galaxies. They are just so far that all we see is all the light that comes from all the stars together. So the information that we have about the Milky Way, the detail tells us a lot about what kind of processes took place in its formation. And what's interesting is that actually some of the stars that we find in a halo around the Milky Way in this region, some of these stars we know, we can measure their ages, they were born around the same time as these galaxies. So by studying stars that are really, really close to us, we can learn about what were the physical conditions in the very early days of the universe. And this is basically what archaeology is about. It's trying to use the fossils, the remains of those early epochs to try to understand, to try to construct the history of formation of a galaxy like ours. So in that context, the Milky Way is a Rosetta Stone. Right? We can use it to disentangle how a typical galaxy forms. And so if you look at the Milky Way, you see it has most of the stars are located in a thin disk. Then there is another component that's slightly thicker, that's in the thick disk. There's a central bulge, and then there is the stellar halo. And because for each one of the individual stars, we can measure how fast they move, we can measure, for example, what their ages are, so that tells us when they were born. We can measure what the chemical composition is of those stars. That allows us to determine in which environment they were formed. And so with all of that information, we can reconstruct history. What's interesting is that the stars in the different components, they are different in terms of their properties. So as I was saying, most of the stars in the halo are old. Most of the stars in the thin disk are still forming today. So we see a range of ages. But not only that, stars in the different components also move differently. So what you see here in white is most of the stars, is that what would be the motions of stars in the disk. And so you see they move rather orderly. And the stars here that are color-coded as red, these are stars from the halo, and you can see that they have much more larger excursions in the vertical direction, but they also move much more randomly. So the stars in the disk move regularly, almost on circular orbits. The stars that are in the halo move on rather elongated orbits. And so this information is something that we can use to identify the different kinds of stars, in particular if we're interested in finding those very old ones, like those that were formed, say, in the very first stages that the Milky Way formed, right? So this stellar halo turns out to be particularly interesting if we're trying to look at, what happened in the very early days of galaxy formation of the Milky Way. Now, it turns out that we live in a very special time today. Over the past decade, our knowledge of the Milky Way has completely changed over the past decade, over the past, say, 5 years or so. So until very recently, basically all we knew about the Milky Way, so we have the Milky Way, if this were the location of the sun in our galaxy, then all we knew about the Milky Way was really its immediate surroundings. We knew how stars were moving, And we knew the ages of the stars, and we knew the chemical composition of the stars. But just for a very tiny region of our galaxy, it is as if, you know, I know Groningen better than I know Leeuwarden. I know Groningen very well, right? I don't know the rest of the world because I don't have access to that information. I only know my place where I live the best. I know where the supermarket is, I know where the pharmacy is, I know what people do, I know where to go if I want to have dinner, a good dinner. I know all of this information, and I can find my way around. But that doesn't tell me about how things are in a different part of the world, right? And so to understand how the full galaxy works, you really need to have access to information over a much larger region of the galaxy. And in particular, you want to have information about what happens in the halo, because this allows us to go very far back in time. So what has happened is that a new satellite was launched recently, the Gaia Mission. This is a European agency satellite that is actually currently measuring how stars move over a much larger volume around the sun. So basically, if this was the neighborhood where we knew how most things about our galaxy, now the volume for which we know this is 100,000 times larger. We have now information. We used to have information for about 2 million stars in this little region. We now have information about 2 billion stars. We used to know how things moved here. We now know that a factor of 100 better than we knew before. And this is really leading to a revolution in galactic astronomy. So the Gaia mission was launched in 2013, and it started observing the Milky Way, basically all of the sky, and most of the sky is dominated by the Milky Way down to a certain brightness. So this is the Gaia mission. This is, of course, an animation, how it opened up. You see here underneath, you have solar panels. That is what maintains it. So it's actually always, the panels are always looking towards the sun. And it's spinning around its axis at a distance of roughly 1.5 million kilometers from Earth. And it moves together with the Earth around the sun. And as it moves, it's actually, scanning the sky. Now, I'm not going to show you, I have a little movie. If you're interested at the end, I can show you how Gaia works. But what I wanted to say is, I want to jump into the science, but basically, as it scans the sky, it looks at it looks at every star that it sees on the sky, so down to, as I was saying, to a certain brightness. And it visits the same region of the sky many, many times. And the stars move really very, very slowly on the sky because they are so far away. But Gaia is able to detect those tiny motions. So even though the stars are moving with 100 kilometers a second, when we look on the sky, the motions are really, really very, very small. So Gaia is capable, just to give you an idea of how precise these measurements have to be, is capable of determining the diameter of a human hair on the moon. So you have to be able to see so sharply to actually be able to measure how fast stars are moving. So Gaia has measured this, what we call proper motions, for 1.7 billion objects. It also has measured for a subset of the stars how fast they are moving towards and away from us. And it's also able to determine how far a star is, so we know the three-dimensional structure of our immediate environment. And with this amazing data set that is absolutely vast, there is really a lot of science that one can do. So you see, these are the different measurements. So basically, every so many years, Gaia has collected enough information that We can use it then to publish a catalog, and this catalog is then available to the whole astronomical community at the same time. So it measures the positions of the objects, it measures how bright they are in, say, normal visible light, the optical, what we see in blue light, in red light. From these two, you can then determine the color of a star, and from the color, you can determine the astrophysical parameters, the physical parameters of the stars. Not only to observe stars, it basically observes everything that's out there down to this brightness limit. So it also observes galaxies, it observes planetoids, asteroids in the solar system. It observes also quasars, very different objects. And so with all of this information, there is indeed a lot of different kind of science that we can do. And that's the reason why this mission is actually making such a huge impact in astrophysics. Because not only can we study, say, solar system objects, so systems, objects around our sun, we can also study how stars near the sun are forming. We can study how, say, the planets around the stars are moving. We can study how the Milky Way as a system is evolving. And one of the things we're finding is that the Milky Way is not in isolation, but it's interacting significantly with its environment. We can use this data to understand the mass distribution in the Milky Way, which tells us about this dark matter. And we can use Gaia to determine, to learn about, for example, very distant quasars. So there's a lot of science, as I was saying, but really the reason that Gaia was built was to try to figure out how the Milky Way was put together. That was the key science goal of the mission. And so big question is, how did the Milky Way come to be like this? So if you want to try to answer that question, then what you need is to measure the motions of stars. Because the motions of stars reflect where a star is coming from. It tells us where they came from. It also reveals the forces that are driving those motions. So it reveals a motion, reveals a force, and a site of origin. And we can use that information and put it together to try to reconstruct history. And that's exactly what we are doing here. So how do we think in general a galaxy like the Milky Way forms? What you see here is a numerical simulation that models the formation of a galaxy like the Milky Way from very early epochs. So that is denoted by this quantity Z, which is known as redshift. So it tells you how far back in time you are. So this is roughly 1 billion years after the Big Bang. And what you saw in the movie at the very beginning was very little, right? And now what you see is small galaxies forming and coming together, being attracted to each other and merging and coalescing to produce larger and larger galaxies. What you see is that even at this point in time, there was already a disk formed here. And most of the action, what you also notice is that there isn't much more action. There aren't that many more mergers at late times. Most of this action happened very early on in the history of this object, right? And that's because the universe was much smaller, so it had a higher density, and so you had a higher chance of meeting other galaxies and colliding with them and coalescing with them. So what you see here at the end of the day in this simulation is that this galaxy that has properties that are similar to those of the Milky Way. And you also see this embedded in a much larger environment, a much larger network of galaxies in the universe. Now the big question is this the way the galaxy formed? Is this really the case? So we have a model, and we don't fully understand all the details of the model. But then what we have to go is go out and test this model. So how do we do that? And this is where galactic archaeology comes in. So this is another set of snapshots from that simulation. So this is roughly 1 billion years after the Big Bang, and you see the small galaxies present. And you see that as time goes by, these galaxies come together, they merge, and something like 8 billion years after the Big Bang, they have merged, they produced a halo. You see that these galaxies get torn apart through tidal forces, and that leaves behind these substructures. And that if you would look at the present day, then you would see a disk in the center of this halo of stars. And it turns out that these stars actually were formed in these objects, right? So if we study these stars and we figure out how to separate them in the different building blocks, then we can actually tell if the Milky Way was built in this way through these mergers. We can also tell how many of these objects came together to produce the Milky Way, and when did this happen, and also how these objects look like. I mean, we don't have access to what happened very early on in the history of the universe directly through observations. All we see is these blobs. So that doesn't tell us a lot about how these galaxies look like. And so one question that we have is, did these objects bear any resemblance to the galaxies that we see around us today? So how do we do that? We use stars. As I was saying, stars are like fossils. In their motion, so the way they move, that tells us the place of origin. In their ages, that tells us when they were born. The chemical composition of a star, the atmosphere, reflects the chemical composition of the cloud in which it was formed. That doesn't change. So that's frozen, that stays in that star. And so that tells us about where, in which conditions these stars formed. And the presence of substructures like this also pinpoint to the debris of the different events. So there's a lot of information that we can use to try to unravel how the galaxy was put together, particularly by looking at the stellar halo. So if I now take this simulation, and instead of just plotting the stars that I see, I plot the stars, but now color-coded by the different objects in which these stars were born, then you see that if you are in the outskirts, if you look in the outskirts of the galaxy, then you can see quite a bit of structure, right? So all of the green stars seem to be together here. There's some magenta stars. So at large distances, you can tell if mergers have been important, because they leave substructure in the outskirts. But as you go to the inner regions, then what you see is the distribution is smooth. So then the question was, how do we tell that really all of this happened in the lifetime of the galaxy? And the way we can tell is through how stars move. So if we take here, so what I'm going to show you here is an animation of what happens to a small galaxy as it orbits a disk galaxy like the Milky Way, but in the inner regions, so very close in, where most of the stars, in fact, are. And so what you see is that this little galaxy gets torn apart through tides, just like the tides that the moon exerts on the Earth, or the other way around. But in this case, the tides are so important that they lead to the disruption of that tiny galaxy. But what you also see is that the stars actually end up distributed rather smoothly. I mean, if they were not color-coded in red, you wouldn't be able to say where the stars were born. But if you look anywhere in space, I'm going to run this again, you'll see that the stars are moving together. If I can run this again. So at any particular location, if we're here, you see that actually the stars are moving together through space. So if I wait a little bit longer, again, here, they're moved together through space, right? So these groups of stars, these streams of stars, through the motions, they tell us that they were not born, say, in the disk, but they were born elsewhere. And so that is when Gaia actually comes in. So if I take a snapshot, I freeze that simulation, and I look at the region around the position of the sun in the galaxy, then what I see is groups of stars crossing, say, the vicinity of the sun with very specific motions in these groups. And so if I have one galaxy that was accreted, then if I look around the solar neighborhood and I plot, I have one group going to the upper right, one group going to the upper left. Then if I plot the velocities, then I see one group going upper right and one upper left. Right? So by plotting just the velocities of the stars, I can tell that these stars were not born in the Milky Way, but was born elsewhere. Now, there's a smarter way of doing this. This is slightly complicated. It's the most complicated slide here. The idea is, so if you think about that satellite in red, so all of the stars were initially together, right? They were moving together through space, and they were in a very similar location. Now, a quantity like energy, so energy in this case measures how fast basically the stars are moving given where they are located. A quantity like energy is a quantity that doesn't change in time. So that little satellite, all of the stars had very similar energy initially. Now, if energy doesn't change in time, that means that if I look at a later time, those stars will have the same energy, independently of where they were. And so then if you plot energy, instead of plotting the velocities of the stars, if you plot energy, and you plot angular momentum, which tells you about the kind of the spinning of those stars around the galactic center, which is also a quantity that doesn't change with time, then you see that all of the stars cluster together again and define a blob in this space. Right? So if I'm after, even if the stars were anywhere throughout the galaxy, if I can measure their energy and I can measure their angular momentum, they will define a clump. Now, we think that the halo did not form from one object, but formed from many objects, right? We think about all of the building blocks that produce the halo. We don't know where the stars come from, right? Stars don't come with flags that tell us, oh yeah, I was born in this galaxy so many gigayears, so many billions of years ago. All we have is a picture in black and white, as it were. But if we then look at the velocities of the stars, then each one of these objects gives rise to a structure in this space of velocity. If we look at energy and angular momentum, then actually this picture that was so messy becomes incredibly ordered, and each one of these clumps is each one of the galaxies that the Milky Way would have or could have accreted. And so then you see that even if I didn't have a picture in color, that if this was black and white, you would, by eye even, be able to identify the different building blocks. Now, we don't do by eye. We would have a clustering algorithm that would do this, right? But that's the basic idea. Now, to be able to make a plot like this, what we needed to have was Gaia, because we needed to know how the stars were moving. We needed to have their velocities so that we could then compute their energies and angular momentum. So then the big question is, what did we find? And so I'm going to spend the next few minutes describing what we found, but I just want to go back to this original picture. So we have the galactic center here, we have the sun here, and we're going to look at how stars around the sun move. Remember that most stars are in the disk, so they move on very orderly on circular motions in the direction of rotation, and they have very little motion in the vertical direction. Whereas stars in the halo, they have very large motions away from the plane. So if we now look around the sun and we look at how stars are moving around the sun, this is what we find. So let me guide you through this. So what I'm plotting here is rotational motion. So that's the motion, the ordered, in principle, ordered motion around the center of the galaxy. And this measures random motion. Now, we live in a disk galaxy, so most of the stars are in the disk. They move like the sun at 220 kilometers a second. Most stars are here. As we move away from this region, we go into the regime of more random motions. So we go into the regime of the halo. And typically, we thought that if we look beyond this red semicircle, we would go into the regime of what was properly the halo. Now, here was the big surprise, the first thing that we found. So most of the stars are in the disk. They move like the disk on clockwise orbits. They move clockwise, actually. But the stars in the halo, you see some fraction moves kind of clockwise, but a large fraction of the stars that have these very large random motions, they actually move in the opposite direction. So whereas, there are a billion stars moving orderly, in one way, then you have these other stars moving in the opposite way, right? It turns out that if you actually look at the properties of the stars that are moving in the opposite direction, particularly the chemical abundances, these stars are different. The chemical abundances are such that you know that these stars were not born in the Milky Way. You know that the vast majority of the stars in the halo that have these very odd motions actually were born in a different galaxy. Were born in a galaxy that was accreted something like 10 billion years ago. And this is a movie that shows that event that was really a milestone in galactic history. This was the last big merger that the Milky Way experienced. What you see here in yellow are the stars from that object that was accreted, and how the Milky Way responded very heavily at that time to that merger, to that coalescence. We can tell when this happened from the ages of the stars. We can actually tell the configuration of that encounter between the galaxy from how the stars are moving. And we can tell how big this object was from the chemical compositions of the stars. It turns out that this is, there hasn't been a merger as big as this one since then. So this was really a milestone, and it led not only to the formation of the stellar halo, because the majority of the stars are indeed in this component, but it also led to the formation of another component that's called the thick disk, because what you see, what happens is that what we had initially is a rather thin disk. Now this disk is puffed up. So this object was really, very important in galactic history. Because of that, we gave it a name. We called it Gaia Enceladus. And there is a reason. So this was a large galaxy that was engulfed by the Milky Way. And, Enceladus is a giant in Greek mythology. It's not, so in that context, a giant makes sense, because actually this galaxy that merged with the Milky Way was very large. So it's good to give it a giant name. Now it turns out that Enceladus is actually in Greek myth, in the myth, is the son of Gaia and the sky. Not only that, but Enceladus is buried under the myth says it's buried under Mount Etna, and it is responsible for seismic activity. And that's basically exactly what Enceladus did with the Milky Way at the time it merged, right? It shook the Milky Way such that it led to the formation of this second component. Enceladus is now buried in the Milky Way, but it was also buried in the Gaia data that we then discovered. So I thought that, this name was really appropriate, particularly that being the son of Gaia and the sky. So have we found other things? So we have identified other smaller objects that have been accreted. We've run recently, with the latest data released from the Gaia Mission, a clustering algorithm in energy and angular momentum. So we use, indeed, machine learning techniques to identify clusters. And we found a very large number of clumps. And if you think about it, so if you look at the velocities, it doesn't look that different from that simulation that I showed you just a few slides ago. So we're on a good track to identify the different objects that led to the building up of the Milky Way. So some have fancy names, like Gaia Enceladus, or Sequoia, or Sagittarius Dwarf. There are a couple of streams that I discovered some 20 years ago. And some have just been discovered, and so have very ugly names still. That will probably change in the next months. But of course, now that we are identifying all of these objects, we really want to know how did they look like, right? And when did this happen? And these are really very early days. But ideally, what we want is to determine something like the family tree of the Milky Way. So if you have the Milky Way today, then it would have merged with different objects at different time. We're finding the remains of those objects, and through the characterization of those objects, we can actually tell whether there were, galaxies like this, they were disky, or they were, roundish, and how that happened. So we are making the first steps into this identification. So this is, at the moment, how the merger tree looks like. It's a bit sketchy, less fancy. But we have identified something like 5 or 6 different building blocks. We sort of know when this happened, and we sort of know how massive they were. These are, like I was saying, it's a sketch. It's the very first days. So what does it take? What will it take to really figure out how this process took place? Well, we need actually more data. All of the things I showed you today are inferences from looking at really stars near the sun in a very small volume around the galactic center, around the sun. So what we need is to use the full potential of Gaia and probe further away from the sun so that we have access to the full history. And that will come with the next releases from the Gaia Mission. What we also need is the chemical abundances of stars. So I was saying these chemical abundances tell us about the chemical composition of the clouds in which the stars were formed. And if you're born in different environments, you have a different chemical fingerprint. And so in that way, you can disentangle the different objects. And that would allow you to go back to characterize those objects, to know how the stars were formed in those objects, but also to go back further in history. What we also need is we only have motions for stars, say, projected on the sky. We know this for 1.8 billion and 1.7 billion objects. What we don't know is how fast they're moving with respect to us. And we really need all of the kinematics, all of the motions to be able to disentangle these rather complex structures. So we need also to get spectra for the stars, for many stars. And in the spectra, what we see is different lines that are associated to the atoms that are there in the atmospheres of the stars. So from these, we can determine how fast the star is moving using the Doppler shift, and also determine the chemical properties. And we're building at the moment several instruments to try to measure this for a large sample of stars, particularly those in the halo. But what is also happening is not just Gaia, but we're also building something that's called the Extremely Large Telescope, the ELT. This is being built by the European Southern Observatory, and this will allow us to do this kind of archaeology, but also beyond the Milky Way. So we can start to go away from our immediate cosmic neighborhood. So I want to show you a little movie of the ELT. Let's see if this works. So the ELT is a telescope that's being built in Chile. It has a mirror that's 39-meter diameter. So this is huge. It's coming soon, means you will probably see the light in 2027. That's relatively soon. And it's under construction at the moment. And you saw in this movie, you saw that there are many different things you can do with such a telescope. In particular, you can study galaxies beyond, in a lot of detail, beyond our Milky Way. We can also try to address the question of, are we alone in the universe? The hope is that we will be able to characterize exoplanets, other planets in nearby stars, to try to understand what their atmospheres look like. Now, this enterprise, as I was saying, this is a large European enterprise. The European Southern Observatory is an alliance of the different European countries, and together we're building, indeed, the ELT. It's going to be the largest telescope of its class on Earth. For scale, you can see here the ELT compared to NEMO in Amsterdam. So you can see how enormous this is, what it means to have a 39-meter diameter mirror at the center. So this is done we have, as the Netherlands, we have a rather strong involvement in the telescope in different ways. So we're involved in building instruments for this telescope. There are 2 instruments in particular where we are playing a key role. And we're working closely with industry, actually, and not only in the Netherlands, but also in other countries in Europe. But in particular, the segments that hold that 39-meter mirror are actually being constructed in the Netherlands. So what's nice in this case, and I think that's a nice example of how astronomy works, is that through this question of, for example, are we alone in the universe, that we're trying to address scientifically, then you push the boundaries of the technology such that you can, make the measurements that will lead to an answer to those questions. Just like I was saying, you want to figure out how the Milky Way was formed, you need to be able to measure the diameter of that human hair on the moon. So we're really pushing the boundaries of technology and taking along industry with a precise instrumentation. But that's not the only thing we do. So to try to work with data sets as large as the Gaia databases, for example, you also need very smart data mining tools. And so those data mining tools should be quick, such that you can explore the data in an easy way, such that you can indeed plot energy and angular momentum and find different clumps, or you can plot how the stars move through space and try to derive the distribution of mass around the Milky Way. But you can use these data mining tools to do a lot more. So this is a package that was developed in my group by one of my postdocs that allows you to do, on a laptop, an exploration of 1 billion points in less than 1 second. Right? So this is quite amazing. And that's what you need if you want to do the science you want to do. So that allows you, for example, to look at the taxi drop-off locations in Manhattan, look at a simulation of structure in the universe, or do a street map of the light pollution in Europe, right? Besides working out how the Milky Way was formed. But what I found particularly touching, and this is something that we discovered by chance, is that this package VAX was actually used as part of the restoration for figuring out what is the best way to restore the Night Watch by Rembrandt. This is purely by chance. So the same package that we use for the Milky Way now is actually being used also for these kinds of things. So the author is Marten Bredels, and he was a postdoc in my group. He now has his own company and doing this very successfully. So that brings me actually to one of my last slides. The work that I presented today would not have been possible without the large collaboration of people that are behind the Gaia mission. So in all of these countries in Europe, there are something like 500 plus engineers and astronomers that work together to produce the Gaia catalogs, to go from those measurements that are so complicated on the sky to a table that anybody can use on Earth. But then also my group, the group of people that have gone through my group throughout the years and that have contributed all of different tools and understanding of how things work, such that when we got the Gaia data, we could quickly figure out this amazing major event in galactic history. So if there's one thing that I would like you to remember when you leave this room and you look up the sky in this clear night, is that actually Gaia is helping us understand how nature put together our night sky. And with that, I will stop. Thank you very much.
Many thanks, Amina. And you surprised me again with some of these stories. Any questions from the audience? We have some time for questions, so please raise your hand and I'll hold the mic in front of you. You can ask questions in Dutch. Amina kan uitstekend Nederlands verstaan, dus als dat prettiger is, dan mag dat.
Ja, dan doe ik het in het Nederlands. Is het mogelijk om bij het jaar 2100 een kolonie op Mars te hebben van 3 miljoen mensen?
Ja, dat is mijn gebied. Ik denk eigenlijk dat het heel moeilijk wordt om zoiets te doen. Ik denk de tijdschalen voor ruimtevaart, ook voor de sterrenkunde, zijn heel lang als je iets wilt bouwen. Dus ik denk, en 3 miljoen mensen, 2100 lijkt me wel heel veel. Dus ik denk niet dat het gaat lukken. Ik denk dat je wat langer moet wachten.
So to be sure, everybody still understands what we're talking about. Are there people who don't understand Dutch? And is that okay for the video as well?
Or maybe you want to translate the question? Or,
yeah, I don't know.
Question.
We're just going to do the 2 languages, I think.
Voor de Gaia, wat is precies de referentie van snelheid en plaats? Wat is het raster wat daarvoor gebruikt wordt?
Ja, Gaia bepaalt zijn eigen systeem. Dus het idee is, omdat je dan de hemel, alle objecten scant, dan kun je gebruik maken van het idee dat quasars, dus zij zijn zover dat in principe niet bewegen. En je kunt het systeem oplossen zodat het een inertieel systeem is. Dus Gaia heeft zijn eigen referentiesysteem.
Quasars bewegen niet.
Die neem je mee, eigenlijk neem je dat als een soort prior. Dus als je wil oplossen hoe het systeem, zeg maar, wat de bewegingen van alle sterren zijn, dan heb je als prior dat quasars niet bewegen. Maar eigenlijk zet je dat, dus ze zitten niet vast. Dus ze mogen ook bewegen, omdat ook Gaia beweegt zelf. Dus je moet ook dat meenemen, zeg maar, als je het systeem van vergelijkingen oplost.
Dus het is een voortdurend elastisch
Ja.
Right?
This big European telescope you were talking about, doesn't it have interferences with the atmosphere? Because I was really thinking this Hubble Space Telescope, I thought this was the summum of possibilities because you are outside the interferences of the sky.
Yeah.
So I wondered what's the gain you get when you build a new telescope on the surface of the Earth?
Yes, that's a very good question, and that's something I forgot to mention. When you saw the little movie, you saw the lasers, right? Those are very powerful lasers. And you can use those to actually correct for the motion of the stars due to the atmosphere. So this telescope is so large that actually the region of the sky that it sees is very, very small. And so you use the lasers to point to a star, it's called a guiding star, laser guiding star, to actually correct for those fluctuations in the atmosphere close to the object you're interested in observing. So that's why you need the lasers. They're not there for science fiction purposes, they're actually there for, doing proper science. So you can correct for that and then get extremely sharp images that are, in fact, because you're doing this from the ground with a much larger mirror, you can actually probe regions of external galaxies much better with the ELT than you can with Hubble.
And they also look cool.
Yeah, they look cool, right? Especially with the music.
Do we know if our sun is born in this galaxy, the Milky Way, or another galaxy?
Yeah, that's a very good question. So we think the sun was born in the Milky Way itself because it has such ordered motion, right? So it goes around the center in an almost on a circle. And that's very, very hard to get if you come from a galaxy from a random direction. Right? So in fact, we think most of the stars in the disk, provided they have these circular orbits, were born in the disk itself.
Thanks. Any other questions? Yeah.
On what time scale do we need to think about the rotation around the center of the Milky Way, the stars?
So how long it takes to, it takes about, for the sun, it takes about 200 million years to go around the galactic center once. So stars around the Milky Way have been, it depends on where you are, say, but have been around about 100 times, 200 times around the center of the galaxy, typically. And the farther out you go, the fewer, say, times they've been around. So also, that's also one of the reasons why if you're looking for this, when you look at the outer halo, you see coherent structures on the sky or in the simulations. It's because these objects have not gone around very often around the center, and so they retain the coherence for much longer.
How many possible Earth-like planets are there in our galaxy?
Interesting question. Yes, so we know, I think the estimates are now that roughly 70% of all stars have have planets. Now the question is, what is Earth-like? So you can define Earth-like by the mass. You can define Earth-like by the composition of the planet. So it has to be, say, not a gaseous planet like Jupiter, but it has to be with dust. You can define also an Earth-like planet by saying it has to be at the right place such that the temperature is such that you can have water in all of its different forms, or liquid water. That is a very Earth-like view. And so we don't know, actually, we're starting to discover that whenever there is one planet, typically there's also a planetary system. So that planets are not formed in isolation. So there's planetary systems like the solar system. Now, many of the planets that we've been able to detect so far are typically very massive and close to the sun, just because through the techniques we are much more sensitive to those. So I think it's very hard to say at this moment to provide a statistic on how likely are these Earth-like planets. But I'm confident that there will be many, and many don't necessarily look exactly like, say, you have a sun. The sun is a particular type of star that emits a lot of light that our eye is sensitive to, but there are planets that around other types of stars that could be at the right distance such that you could have, for example, liquid water. So it's not quite the exact sibling or equivalent of the Earth, but it might be rather similar. And so we're discovering these objects, but we don't yet have the technology to understand whether there is an atmosphere around these objects and what the properties are.
If the Milky Way interacts with dwarf galaxies, do all dwarf galaxies merge with the Milky Way, or are there also some who pass through the Milky Way because of the size?
Yeah, that's a very good question. So the Milky Way has its own system of satellites of dwarf galaxies, and they are not apparently being destroyed by the Milky Way. They seem to have been there for a long time. And that's probably because they're sufficiently far that the pull that the Milky Way exerts is not large enough to actually destroy them, tear them apart. So indeed, they do survive. On the other hand, there are some dwarf galaxies that are coming close, and we're seeing them disrupt at the moment. We're actually seeing a few of those. And in the near future, we will actually merge with the Large Magellanic Clouds, which are one of the galaxies that was shown in the we can see actually with the naked eye.
So if I say the near future, this is next week, Tuesday or something like that, I think you have a different time scale?
We think on different time scales. So near future is a few billion years from now.
What do you hope or expect to find with the data from the new extremely large telescope? Will it be more precise data or something completely different?
Yeah, so this that's the amazing thing about this telescope is that there's so many different areas where it's going to have an impact. And so one of the areas is indeed, I think, the exoplanet, so the characterization of the atmospheres, just observing the atmosphere, observing the light from that planet directly and figuring out the chemical composition of that atmosphere. That's going to be absolutely amazing and I think totally revolutionary and will have an impact far beyond astronomy. So that's one of the reasons we're building this very large telescope. But also to try to understand, I think there are many open questions also related to the Milky Way and related to how the different chemical elements have been formed throughout the history of the universe. So, I said at the very beginning, we formed initially in the Big Bang only hydrogen and helium form. But if you look today, we have, carbon, iron in our bodies. How did those form? How did that process take place? And we know it happens inside stars, but we don't know exactly how and when this happened, in what kind of environments, in neutron stars, in mergers of neutron stars. So there are many questions about stars, about galaxies that a telescope like this will actually address. Yeah, thanks.
So thank you, and I think that might also be a nice way to round up the evening, a look into the future and the things you still hope to discover. Thank you very much, and thank you again, Amina.
Thanks.
Wel thuis.